So the main idea of gradient descent algorithm was the infinitesimal neighbor area follow a linear function like this. L theta is equal to L theta t plus gradient of L as theta t and theta inner product. For the theta belong to very tiny area minus epsilon to plus epsilon. Here epsilon can be a vector. Okay? So all one vector filled with epsilon. Right. So when epsilon is very close to 0, then we have this almost linear property, and the gradient descent algorithm can guarantee always decreasing property. So we can expect very nice loss value after sufficient number of iterations. But this approximation does not hold when the update, so theta t plus 1 minus theta t is huge, this is huge, then we cannot guarantee the monotonically decreasing behavior. Okay, so for this, we can think this type of approach. We can think some optimization problem, so minimize the linear approximation function with respect to theta with constraint theta minus theta t less than or equal to some delta. So when you set the delta, the big delta close to 0, then the L bar function, the linear approximation function, will be very close to the original loss function. So the gradient descent algorithm can guarantee the monotonically decreasing property. And the answer, the solution of this optimization problem will be theta t minus delta over norm of gradient L theta t times gradient L theta t. So when you set the gamma t equal to big delta over norm of gradient L theta t, you can guarantee that at each update, the update ranks is always equal to delta, big delta. And then when you set the big delta equal to very tiny value, then we can say the monotonically decreasing property with the gradient descent algorithm. And so we can guarantee the convergence behavior. Right? So this is one possible approach, but in practice, we really don't like this approach. We don't use this. The main reason is this is very slow. Okay, so when you set delta is very small, 0, if the initial value x0 is far from the x star, the optimal point, we need this amount of iterations to reach to the x star, because at each time we can move at most delta times. So we have to learn at least this amount of iteration to have a very nice result. So when you set delta tiny, this is huge. Your learning time will be extremely huge. It's too slow, right? And also this idea. So in the previous page, we use this update rule. We divide by the norm of gradient vector, and actually I don't like this idea. Why? Let's consider a very simple convex function like this. Again, there is only a single parameter, input parameter, and then we can easily notice this is an optimal point, right? So when the zeta t is here, basically our distance to the optimal point is huge. We have to move a lot, right? But when you always normalize your update by the norm of gradient vector, you always restrict the amount of update, right? Which make your convergence very slow. But when you look at the gradient, when the value is far from the optimal, usually the gradient value also huge. When you as you close to the optimal point, the gradient value becomes small, right? So when we utilize this property, maybe we can improve the conversion speed. So instead of normalizing this norm vector, we can just simply use gamma times L gradient of L zeta t. Personally, I'll buy this idea. And theoretically, there are many convergence speed result analysis, especially for convex function. With this constant step size, we can guarantee some nice things. Okay. So to say about the convergence speed, I have to say about the smoothness. When your function is smooth, so smooth means the gradient of your loss function at point zeta and the gradient of your loss function at zeta prime is upper bounded by the distance between zeta and zeta prime with a constant, let's say alpha. Then this function for all zeta and zeta prime, then the loss function satisfy alpha smooth property. Okay, alpha smooth property is very important to guarantee something with gradient descent approach, especially when you set the step size gamma is equal to 1 over alpha. We can guarantee many nice convergence behavior. Okay, this is very important. So why smooth is important? When your function is not smooth, like this, here the slope is very huge, but here slope is very small. But here again slope is very huge, extremely large. Okay, then when you set a very small step size, right? Very small step size. In this area, your update is too tiny, so your the gradient descent update becomes very slow. But in this area, the tiny step size is okay. When you use a huge step size, the step size is good for this area, but the huge step size is very bad for this area. When you use some high value for your step size, with this area, you will see some huge jump. Okay, it will never converge. So smooth behavior, the alpha smoothness is very important to guarantee something for your gradient descent algorithm. And theoretically, it is believed that the step size equal to 1 over alpha is kind of the point, kind of optimal point. Okay, but the problem is we don't know what is alpha. It is extremely difficult and it is almost not possible in practice to know alpha from your loss function, right? So in practice, we actually set gamma as an hyperparameter and control the hyperparameter using some cross-validation, trial and error. Using many experiments, we empirically find some nice gamma values, nice step size or learning rate that can train your neural network very well. And we can introduce some nice time-dependent gamma as well. This is called learning rate scheduler. And many papers are dealing with the learning rate scheduler. Still, there are many interesting open questions. What is the optimal learning rate scheduler and how to optimize the learning rate scheduler and so on. Even recent machine learning conference like ICML, NIPS, or iClear, there are many papers studying this hyperparameter optimization or learning rate scheduler things.